feed. And in the background, Grant, who's sitting probably, 20 offices down that way, is taking it and sending out to YouTube. So let's give Grant a hand and thank him. All right, we got the lights. You can bring the lights down and we'll set and we'll get ourselves started. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. It is my pleasure to host tonight. I am Dr. Frank Summers of the Office of Public Outreach. And it's, somebody stole my lithograph. All right. So when you come in on the tables, we have lithographs, pictures from Hubble. Tonight's picture is Messier 104, the Sombrero Galaxy. And I chose it because it has a very large central region. That's the bulge of a galaxy. And you're going to learn about the bulge of the Milky Way galaxy tonight. Tonight's speaker is talking on the Milky Way's bulge from a hypothesized blob to a remarkably detailed picture, okay? So you have an example of a bulge in front of you to reference while he gives his talk. Next month, Greg Sloan will be talking about ashes to ashes, dust to dust, the fate of stars like the sun. So he specifically said he's not going to talk about exploding stars and black holes and neutron stars, because that's another talk. He's going to talk about what happens to medium-sized stars like our sun, and the ashes to ashes, dust to dust is a clue, okay? So come back in August for that. In September, we will talk about more death. We're just being morbid here in our astronomy. 100 ways to die in the universe. That's Katie Alatalo. We'll be talking about that. And in October, then we'll get to those exploding stars. We'll talk about chasing supernova with Kepler from Gautam Narayan here at Space Telescope. If you would like information about these, you can go to our website, go to your favorite search engine, type in Space Telescope Public Lectures. You should find this webpage with our upcoming lectures listed here, the links to our live webcasting, as well as our archive. The YouTube playlist goes back to 2014, and the STSCI webcast archive goes all the way back to 2005. So there's an awful lot. If you want to binge watch astronomy lectures, I got an entire week of it for you, okay? Actually, I realized that, tonight is probably about my 16th anniversary hosting these public lecture series. And I just want to say thank you to the audiences, because, it's been a lot of fun. But wow, 16 years. Woo. All right. If you would like to have notice about these public lectures, you can sign up by providing your email here to our announcements. We send out like 2 or 3 announcements a month. Yes, announcements, sign up at the website, or if you can't handle online technology, what are you doing asking for an email? But anyways, just give me your email address, write it down on a piece of paper, and I'll make sure to add you, okay? If also you have comments or questions, you can send them to our email, publiclecture@stsci.edu. If you are into social media, we have a variety for the Hubble, Webb, and Space Telescope on Facebook, Twitter, YouTube, Instagram, and probably a few others that I'm not listing here. I myself am on Facebook, Google+, and Twitter every now and then if you want to hear more from me. Let's see. Observatory. I did not get an email before I started this. It was sort of cloudy and sort of not cloudy. Actually, when I left my house to come in this evening, it was raining, but it was sunny while it was raining. So I'm not sure what we're going to do. So that's still a question mark. I will check with Irini during the lecture, and I'll have an answer by the end of the lecture. Okay? But if you are not, if it doesn't happen tonight, remember there are still open houses on Friday evenings. This webpage of the Maryland Space Grant Observatory will list the observatory status every Friday evening about 5:30, 6 o'clock. They will list the status, whether or not they're going to be open. So if you don't get a chance tonight, check back on Friday. And now the news from the universe for July 2018. And unfortunately, I have a repeat story for you tonight, and it is a JWST launch delay, okay? So, last time, back in, let's see, when was it? It was in March or April or May, one of those, about 3 months ago, okay? The status of it was that it was being delayed until May 2020. They had formed an independent review board to look at JWST's construction and really go through the process rigorously, and especially to do a new cost analysis to make sure that they really knew what it was going to cost. Well, that independent review board has now finished its study, and the press release from last week was that they have a new launch date for Webb of March 30th, 2021. So that's another 10 months of delay for the James Webb Space Telescope. Why? Well, there are changes in the schedule due to environmental testing and work performance challenges on the spacecraft's sun shield and propulsion system. Okay, that's technical language. The environmental testing, I believe, is the vacuum chamber testing that they did down at Johnson. Okay, and so they need more time to pass all of those tests and to get things together. However, the independent review board, I mean, this is independent. This is not a NASA board. This is independent of NASA. They came back and they also reaffirmed Webb's significant complexity, incredible scientific potential, and importance to astrophysics, okay? So they didn't say like, oh, no, this is a problem. No, they said, look, this is really important and we gotta get it right, okay? We do not have any chance of servicing the James Webb Space Telescope. You're gonna get it right the first time. So that's basically what they said. And the new development cost estimate is $8.8 billion. And for those of you who remember what I said a few months ago, the development cost estimate originally was $8 billion, so this indicates a 10% increase in that, okay? And that's basically the summary of the press release. We are, of course, disappointed that we'll have to wait longer for the science from the James Webb Space Telescope, but it's the next great observatory, okay? It's going to do things that Hubble can't do, that no other space telescope has ever been able to do. It's highly technical, and as they say, it's going to be worth waiting for, okay? Let's make sure we get it done right. All right. Our second story tonight is It Came from Outer Space. I am talking about yet another update. The object called A2017-U1, also now called Oumuamua. This is the orbit when it was discovered in October 25th. Actually, it was discovered a little bit before this in 2017 by the Pan-STARRS Observatory. All right, and if I pull back, you can see this is the full path of it. And what makes this special, which makes this U1, okay, is that this object's path is unbound to the sun, indicating that it's not part of our solar system. It came from outer space. Yes, this is the first confirmed object that trajectory comes from interstellar space. All right, and there probably have been many of these that come through our solar system. This is the first one we've seen and confirmed. And when I told you about this last fall, I showed you that, hey, this is all we can see of it. Yeah, that tiny little dot there that the arrow is pointing to, that's Oumuamua, all right? So it's really small, okay? It's only about half a mile in size, and that's just an estimate, okay? And we're looking at it, and so we really can track it, right? But you need high-precision telescopes to track it. Gee, where would we have a high-precision telescope? Yes, Hubble has helped. The other thing that we noticed about it is also that it had brightness variations, periodic brightness variations, indicating that it was rotating and very likely was very elongated. It wasn't like a round object, okay? If a round object rotates, you don't get these strong brightness variations, but a elongated object rotates, you get these strong brightness variations. So what we knew about it last time I talked about it is that its orbit is consistent with an interstellar origin. It rotates about every 7.3 hours, and there are these large brightness variations. What we didn't know back then was its size, about half a kilometer. The axis ratio, was it 3-to-1 or was it 10-to-1? The color and the amount of reflectivity, which is called the albedo, the measurements appeared to disagree. We didn't know what it was composed of. Is it more asteroid-like? Is it more comet-like? And this is only the first one of this group. What are interstellar objects generally like? And I finished with this slide, to be continued. Tonight, we continue the story. Tonight, I'm going to show you an artist's rendition of what Oumuamua looked like on January 2nd, 2018. So this is the artist's rendition of Oumuamua here on the left on January 2nd, 2018. And how do I know it's January 2nd, 2018? Because you see those positions of those planets? Yeah, I calculated them, okay? I made sure that where Oumuamua was, we got the planets right in the background. I also calculated the position of the stars in the background, okay? So this is the star Spica in the constellation Virgo, okay? So not only are the planets in the right place, the stars are in mostly right place. I can't say it's absolutely the right place, okay, due to various things we did with the artistic aspect of it. But, all right, so this is relatively scientific in being an art. We try to combine science and art here, okay? And then you can see that there's all sorts of fuzz around it, okay, and these jets coming out of it. And that is the real story. So, in watching Oumuamua over the past several months, okay, and basically the observations ended in about January, they found that its orbit deviated from what would be expected just due to gravity. Now, gravity is a solved problem. We know how to solve gravity. So if an object moves off of a path that gravity would predict, some other force is involved, okay? So there's just a slight acceleration, but we can measure these slight accelerations. And it could be caused by jets of outgassing, right? And that would be the ices near the surface spewing out as it passes by the sun and heats up, okay? And so that's why you can see there are jets here in this artist's illustration pointing towards the sun that would add a small force that would cause a deviation in the orbit. This is similar to what we see for comets in our solar system. However, the important point to note is that no outgassing was observed, which causes a little bit of a problem. So you need some outgassing to create the orbit deviation, but not so much outgassing that it would actually be observed by the telescopes that looked at it. There's still lots of uncertainty here. We still don't have great estimates. We still only have estimates of the size, the shape, and the composition. But if this outgassing is true, then it's probably more comet-like than it is asteroid-like. And unfortunately, we're not going to get any more observations because now it's out past the orbit of Jupiter and heading out of the solar system, never to be seen again. So, where do we go from here on this? There should be other interstellar interlopers in our future. If there's one, there's got to be more, right? And now we know that there is a population. We will continue to look for them. I sort of think of it like the Kuiper Belt objects. When we saw the first recognizable Kuiper Belt object in 1993, we started searching and searching for more and more, and we developed a whole family. Hopefully, over the next years and decades, we'll develop a whole family of these interstellar objects, and we'll be able to understand the characteristics of a population. One is just an interesting object, but until you have a dozen or so, then you can't really make group statements. So we look forward to more interstellar visitors. I wish they'd hang around a little bit longer, but the nature of their orbits means that they're going to come through, bam, we get about 6 months of observing, and then they're gone forever. All right. Finally, our third story, a 10 million year old baby. This just hit the news wires today, okay? And I could not stop myself from adding it to the public lectures, the presentation. All right, so this, somewhere in here, is the star PDS 70. I'd love to point out the exact star, but they didn't tell us when they put out this image. They said, "Oh, it's in the center." Well, this is the center. I don't know exactly which one it is. All right, and so the star PDS 70 is special It's, well, first of all, it's an ordinary case 5-star, but it's only 10 million years old. It's a young star. It's a recently formed star, okay? All right, for PDS 70, all right? And in 2006, they did a study of PDS 70. All right, so this is the star, all right, and they're blocking out a little bit of the light from the sun with this occulting spot. You'll notice there'll be a black circle at the center of all these images. That's not because there's nothing there. It's because we're actually blocking it out. That black circle is blocking the light from the star, okay? So here's the star. Here's a potential companion that they identified, okay? And when they analyzed this and did all sorts of computer processing and pulled it out, they found that, first of all, that this star was a brown dwarf that could be a companion, all right? And then they found a disk of material orbiting around the star. All right, so you're seeing a disk of material edge on, right? So you're seeing material orbiting around the star, plus a jet of material spewing out perpendicular to the disk. And we see this in other places. For example, in Orion, when we see newborn stars, okay, we have disks and we have jets. All right, and so this was interesting, and there were strong hints that a giant planet could have formed in the interior, in the inner parts of the disk. They went back and studied this again over time, and in 2012, they released this image. Again, this black spot is just the occulting circle to get rid of this light of the star, but you can see how there's a bright ring here, and inside the ring is an empty region. Okay, there's a gap that's about 140 astronomical units across. And if you don't remember, an astronomical unit is the distance from Earth to the sun. Neptune is about 30 astronomical units in radius, so this is 140 astronomical units, okay? And so there is a gap in there, and that really says, hey, if there's a giant planet in there, or one or more giant planets, that can clear out that gap. Well, that sets the stage for what was just announced. In 2018, they got a picture from the Very Large Telescope. Yes, that is its name, the Very Large Telescope. We astronomers are pretty straightforward. From the European Southern Observatory, the VLT got that image. You can see the gap, and you can see that. Ladies and gentlemen, this is the first confirmed image of a newborn planet. This planet is called PDS 70b, the lowercase b indicating that it's a planet. It's about 20 astronomical units from its star. It is a few Jupiter masses, so only 2 or 3 or 4 Jupiter masses. All right, so it's Jupiter sized. It's a gas giant planet. It's very hot, okay? 1800 degrees Fahrenheit, all right? For example, the cloud tops of Jupiter are minus 100 degrees Fahrenheit and such, all right? This is still in formation, okay? 10 million years old. This is the 10 million year old baby I was talking about in the title, okay? And when they do further analysis on it and they really study it, they can tell that its atmosphere is cloudy. I can't tell you how, because I didn't have enough time to read all the papers today but that's one of the results that they came out from it. So we have had pictures of planets and such, but this is a newborn planet. It takes approximately 10 million years for a gas giant to form. So this is really just a newborn gas giant, and it's a really cool result that just got announced today. All right, so I like to bring you the really cool results as they come. Even though this isn't a Hubble or a Space Telescope story, it was just too important to skip. All right, and that's our news from the universe. Our featured speaker tonight is David Nataf from the Johns Hopkins University. He did his PhD work at the Ohio State University, and then did a postdoc down in Australia. Although he says he originally hails from Canada, came to the U.S. to do the PhD, went to Australia to do a postdoc, and fortunately came back to the U.S. to the Johns Hopkins University, and he holds the Davis postdoctoral fellowship across the way. He'll tell you about his research, but he says that in his spare time, when he's not doing research, he works with the summer interns, that the high school and college students that come in and work with us over the summer. And he's also can be found down at the SPCA walking the dogs. Ladies and gentlemen, David Nataf. There we are. Cool.
Okay. Thank you for the introduction, Frank. Can everyone hear me? All right, good. All right, so I'll be speaking about the Milky Way's bulge, and I'll explain what a bulge is shortly, but you can see one in the image that was given out earlier. That's the Sombrero Galaxy, relatively famous galaxy, and that is a spectacular image of a galaxy which is a combination of a disk and a bulge, somewhat similar to the Milky Way, but not quite. This is an image that'll look very familiar to people who have gone camping, and maybe not familiar to people who have never been outside the city. That is what the Milky Way will look like from the ground if you don't have light pollution and if you have decent night vision. Okay. And I heard an interesting anecdote a few years ago. I don't know if it's true, but it sounds like it could be true. Apparently, many years ago, there was a huge power outage in Southern California, and then people saw this, and they had no idea what it was, so they got scared, and they called police. There you go. So here's two images of the Milky Way panoramically in optical and near-infrared photography. I'll explain what... So optical is the type of light that we can see. We can see, it goes from blue light to, and then you got green light, orange light, and red light, with a bit more detail. Actually, I skipped purple light. And this is near-infrared light. And can somebody point out, so you can all see that it's kind of the same, but there's some differences. Could somebody point out a difference between the top image and the bottom image, other than the kind of light they're in? Yes? Yeah, so there's all these dust lanes in the top image. It looks like it's black, but it's not black. There's a ton of stars there. Just a lot of the light is blocked out by intervening dust particles. And dust, it kind of affects all lights, but it affects bluer light a lot more than redder light, or optical light a lot more than infrared light. I learned something cool when I lived in Australia, which is kind of, after it was explained to me, it was obvious. So in the southern hemisphere, they do see more of the Milky Way due to how things are oriented. And for the Australian Aborigines, their constellations weren't just, connections of stars. The dust lanes themselves could also be constellations. They would make animals out of that, and as it moved through the season, it would correspond to different parts of the fertility cycle. All right. So here's the Milky Way bulge, or rather actually it's a whole galaxy including the bulge as part of an artist's rendition. And some of you may feel I'm being cheap right now. I'm showing an artist's rendition of our own galaxy. Can someone tell me why I wouldn't be showing a photo of our galaxy? Yes, in the back.
Because you need to travel so far out to get it.
Thank you. That's exactly right. Yeah. So the previous images were kind of like in the galaxy to see that, right? But really we're only seeing, we're like 70 or 80% outwards. So in those images, we're kind of seeing the inner 70% of the galaxy. But here, it's what somebody, if you've traveled like 10,000 light years outwards, and it's worse than that, because if you did go out by 10 or 50,000 light years, good luck sending the signal back. You'd be like, uh-oh, how did I end up here? Where do I go? You'd be screwed. And so in this image of the galaxy, the part that's real, so it's a very idealized image. The real galaxy is probably not super symmetric. Many galaxies are symmetric, but not perfectly so. But the part that's relevant here, the spiral arms are in blue, and the bulge or bar is in yellow. The reason it's a different color is that there are fewer young stars in the bulge, and I'll discuss that at the end. So now we're going to see a video of a forming galaxy. There's so many videos of galaxies forming out there. I didn't know which ones to take, but I took these two. There's this one and another one afterwards. We're going to watch this go. It shows Z on the top left. That's a cosmological redshift that corresponds to time. Z of 15 means about 13.5 billion years ago. Z of 1 means 7.8 billion years ago. And the way galaxies form over there, they're believed to have formed from tiny proto-galaxies, maybe 1,000 or 10,000 times smaller. And as the universe ages, they all come together, and eventually we have a disk like we have now. This picture is definitely accurate, but the details might be off. It's a matter of controversy. And so we see, by this point, most of the galaxies assembled. There's kind of fewer big pieces coming in now. There's still a lot of small pieces, like for our own galaxy. But, the big things are there. And the Z thing has slowed down, so it kind of looks like maybe the computer got slower because it's too complicated, but that's not it. It's just the way Z is defined. As you go from Z of 15 to Z of 5, you only travel 1 billion years. But as you go from 5 to 1, you go like 8 billion years. It's kind of the mapping between the history of expansion of the universe and the actual age of things. And now, point 4 is about when the sun formed. So this galaxy here would have a baby sun if that was like the Milky Way. We see that it's a reasonable spiral. It's not completely symmetric, but it's pretty close, right? Like if this was a flower, it doesn't look like a flower, but pretend it does, it'd be kind of a pretty flower. And unlike our galaxy, this one has a pretty big merger going on at the end. Our galaxy now only has, it has small mergers going on right now. Ouch. That's our galaxy in 2 billion years when it merges with Andromeda. And now here's a second galaxy, and it already started. It looks the same at first because they all look, did I actually, no, sorry. Okay. This is actually what I meant to look at. Okay, this is just this galaxy, the point of it is that it's thought to be more similar to what the Milky Way might have gone through. Of course, these are random realizations. You could go through it 1 trillion times and never find a match. But you'll get a qualitative match, which is similar statistically, so to speak. All right. So in this image, we see the light of gas and stars. Stars form from gas. What we're not seeing is the light from dust. It's just turned off in this video. The dust is still active and having physical effects, but it's turned off because the video is meaning to emphasize the gas and the stars. And what they bragged about when they made this is that they're able to make a pretty thin disk. The people who simulate these galaxies have been able to make disks of galaxies, like the Milky Way has, as I showed you earlier, for a long time. But to make thin disks, crepes rather than pancakes from Blue Moon is a bit hard. And galaxies are more similar to crepes than to pancakes from Blue Moon. Maybe not in this image. But yeah, this has a pretty thin thin disk, and you can see that there's a bulge already. And so to go through why bulges matter, really the whole galaxy matters. You might come to another talk a year from now. They'll be talking about the disk or the outskirts or the star clusters. Every part of the galaxy matters. The reason that the bulge matters is that it's many of the oldest stars in the galaxy. That's why it's yellow. And so by understanding that, we can have a pretty good idea of how a disproportionate number of the first stars formed. Even though it's only 1/3 of the total stars, It might be like 1/2 to 2/3 of the oldest stars. And I make a lot of analogies with history. The field is now called galactic archaeology, maybe for marketing reasons. But imagine in history, like you knew about, the American Civil War and the Spanish Inquisition and that interesting stuff, but you didn't know about the Sumerians and the Greeks. Your knowledge would be very incomplete. You need to know that stuff is interesting as well, and it helps complete the story. All right. So part one is the shortest part. It's the chemical characterization of bulge stars. It's short because, there's 3 parts in here. There's chemistry, there's structure, and there's ages. And chemistry might be the simplest in that it's reasonably solved. I don't have as much controversy to share for you. It wasn't solved maybe 30 years ago, but it's solved now because we have these great new instruments. We could look at hundreds of stars at a time. This was taken by a PhD thesis in Australia. Who knows what Fe might be? That's right. So the distribution, the metallicity of stars is usually, it could be any metal. Why not copper? Why not zinc? Iron is used because it happens to have a lot of atomic transitions. And so you get a ton of lines when you look at the atmosphere of a star, absorption lines that are due to iron. And in fact, if you go back 100 years, a lot of astronomers back then, so they didn't have quantum physics understood, but they knew that, so they didn't really know what was going on in the solar atmosphere. They thought that the sun was made of iron, because iron makes a ton of absorption lines. But that's not it. It's just, it just happens that at the typical temperature of a star, iron has a lot of transitions, and so we use iron to measure things. All right, so here it's a logarithmic ratio of iron to hydrogen. -1 means 1/10 the iron to hydrogen ratio of the sun, and plus 0.4 means about 4 times the iron to hydrogen ratio of the sun. And it turns out that almost all bulge stars are in that range, and the typical value is 0. I always think that this is a big coincidence, but the metallicity of the sun is very typical of the metallicity of most of the stars in the bulge and indeed elsewhere in the galaxy. It's a little higher, but I don't know. I think it's cool that the sun is such an average star in metallicity, where metallicity in chemistry is a thing that varies the most between different stars. And we can also study other elements. I could go on and on with other elements, but it'd be like too much information. And to be honest, the other elements aren't measured as well, so it's not as informative. But here we show O, Si, and Ca, calcium. So oxygen, silicon, and calcium. And it's the ratio relative to iron. And what's been confirmed over most decades of research, the past 20 or 30 years, is that the ratios are higher in bulge stars than in the sun. So this is one place in which, one area in which bulge stars are different. They just have more relative abundances of these elements. And that's kind of cool. Imagine you form an Earth there, right? And Earth is, I think iron is the second most abundant element after oxygen in the Earth. And so imagine you truncated that in half. It might have a different evolution of life going on. And the reason for this is thought to be that the bulge formed quickly. That's why it was yellow in the previous images. The stars are older. And therefore, it has more of those kinds of supernova. All right, I'll skip this slide. Structure of the bulge. Has anyone seen an image like this? All right, so this is the Hubble tuning fork diagram, and it kind of shows that galaxies come in a huge variety of shapes and sizes. It was first written down by Edwin Hubble approximately 100 years ago, and he had some story about it, about why this happens. That doesn't hold up. That's fine. He didn't guess the reason, but what's interesting is that we still don't know the reason. Well, we know a little bit, but not really fully, why galaxies come in these shapes. And when astronomers realized that there were galaxies, They didn't realize what kind of galaxy the Milky Way was. Is it one like this, like this, like this, like this? Of course, you guys might guess, because I showed you an image earlier of an artist's rendition. Does anyone want to point to one of these? Or I don't know if it's big enough for everybody to see, and say which one is most similar to the Milky Way. Yes, who said that? Yeah, down there. Probably this one, maybe this one. So the bar, as I'll explain soon, is reasonably well understood. However, the spiral arms are not that well understood. And maybe I will show you great images of the bar shortly of what it could look like. It's one of the achievements, not shortly, but maybe in 5 minutes, one of the achievements of astronomy in the past 10 years. But the spiral arms, not yet solved. All right. So the Milky Way is not an unbarred galaxy like the Whirlpool galaxy. This is an image of a typical unbarred galaxy. It might have a very, very weak bar in here. That's possible, but it'll be very weak, so whatever. Can somebody tell me something else about the Whirlpool galaxy that's different from the Milky Way? Yes. It has a companion right here. The Milky Way does have companions, but nothing that's like a quarter the size like that. The Milky Way is a barred spiral galaxy like NGC 1559. Maybe not quite exactly like this. This is a very strong bar. We see there's a lot of dust lanes, just like in our galaxy. And if I could ask another question for you guys, so the question is on the screen, why is it that this galaxy, the ones I showed you before are circles, but this one here appears to be longer in one axis than the other axis. It's like twice the length. Does anyone have a good guess as to why that might be? Yes? That's right. Of course, it could actually be that it is slightly asymmetric. That does happen. There could be a companion just off that's torquing it. But the most likely explanation, you take something that's flat, you tilt it, and then it'll appear longer in one axis than the other. The Milky Way is the only galaxy that we can study in 3 dimensions. All other galaxies appear as 2-dimensional projections. And another image, this one is more plausible. The Milky Way is a barred spiral galaxy like NGC 4394. This one's 54 million light years away in the constellation Coma Berenices. No one's going to remember that. That's okay. What's cool about this one, this is such a strong bar. This is like really strong, and it's actually kind of similar to the Milky Way's bar that we're going to see in a few screens. Somebody said something. Yes? Oh, sorry. Okay, so let's go back here. So bulge is like the central part. If you think of a disk of the galaxy as a pancake, in the middle of the pancake you can have like a pile of whipped cream or butter. Or, I don't know, spinach. But, so that can take on different shapes, apparent shapes, depending on the dynamics and the gravity and the interactions with neighboring galaxies. And sometimes it's just a big blob in the middle, like in these, or in fact, like right here. And sometimes you end up with a barred shape like this in different contexts. It really depends on the history of the interactions. I'll get to that soon, but thank you for asking that. All right, we were on this one. And okay, so we didn't always know if the Milky Way's bulge was a bar shaped like a bar, like this, right? Or if it was shaped as a spheroid, like this. It's hard to guess, and you go back 30 years and everything was less precise and there was less data. The first really good evidence came from Stanek and al., 1994, Chris Stanek. Then he was a graduate student at Princeton. And imagine that we're in this artist's rendition. If you look at the stars here, and then you look at the stars here, the ones that are here, because they're closer, are going to be brighter. Let's say they're like 30%, if they're 20% closer, then they'll be about 40% brighter. And that's what he found when he looked at a tiny, what is comparatively to now, a tiny amount of data. He was able to discern this. These three histograms are meant to show that stars are slightly brighter over here than over here. And from that, he called it evidence for the galactic bar. This was done with Polish astronomers. Here I show a photo of him. It's an interesting anecdote about the referee process in science. This was somewhat controversial. People thought the Milky Way had more of a bulge like this, a spheroid. And I think the first referee either challenged it or rejected the paper. He said you cannot submit a paper on the evidence for the galactic bar because there is no galactic bar. So, okay. The process of peer review, which we hear about in the media and the newspaper sometimes, is making science sacred. It's really good. It does help things, but it's not perfect. Something that helps in general will have instances where it either helps something bad or blocks something good. Though in this case, they were able to get to another referee, and that's fine. You do get second chances because it's realized that this can happen. But, that was kind of a coarse image that Stanek got, right? He said evidence for the galactic bar. That's great. But if we want to know what the Milky Way looks like, right, we need a lot more than evidence, right? I mean, both of these have evidence. They're different. Which one's the accurate representation? We'd like to know. And one thing that's helped is the improvements in CCD technology. I remember when digital cameras first went on sale, or maybe when the second went on sale, I probably missed it first. You had like 3 or 4 megapixels, and that was good, and it was like $500. No, now you could get, I don't even know what it's up to now, maybe like 20 megapixels for $200 or something. It's just improved very rapidly. And the same thing is true of astronomy observatories. Whereas they used to use, the data that Stanek used was 5 megapixels. It was from the Warsaw Observatory located in Chile in South America, about a few hours north of Santiago. Now we regularly use cameras in astronomy that are a few hundred megapixels. This is a CCD, charge-coupled device. A single one of these has more pixels on it. Actually, this is the CCD, charge-coupled device. You see there's many of them together. They tile many of them together because it's easier to do it that way than to make one big one. And a single one of these has more pixels on it than the camera that was used to confirm the existence of the bar in the 1990s. It's really improved rapidly. And here we have an image of the sky here. It's great. And then there's another coincidence that as much as cameras have gotten bigger, right, at about the same speed, hard drives have gotten bigger as well, right? I remember playing computer games in the 90s. If you wanted to play one game, you'd have to delete the other game first. Hard drives were really small. And I think the teenagers here, have any of you ever done that? Wow. Okay. Well, I had to do that all the time. And, going back here, imagine CCDs had grown much, much faster than hard drives. That would totally suck for astronomy because we would take these great pictures and we wouldn't be able to store it. Okay, so there's like 100 times more data now, and people have used it properly. And this is from Christopher Wegg, who did a postdoc in Germany, but grew up in the UK. And it's a deep projected model. So same methodology of Stanek, slightly more sophisticated, but just hundreds of times more data. And this is a deep projected model. This is what the Milky Way's bar would look like face on. This is what it would look like side on. And this is kind of what it looks like from the sun. What happens is here, okay, so if the sun is here, we see this, and then like this side here is taller than that side because it's closer. But this here, the second image, is what you would see if you were living right here, if the sun was there. They'd see both sides symmetrically, and it kind of has like an X shape or a peanut shape. It's a really remarkable image. In 20 years, we've gone from rejecting papers that said that the galaxy might have a bar to having a really precise deprojection of what the bar looks like. I think that's a great achievement. And then you might say, okay, that's from a model. There's a lot of analysis going on. I don't trust it. It's too complicated. Computer models will give you whatever you want. Okay. Well, that's sometimes true. In this case, I don't agree because I know what went into the model. But here is an image not taken in the not from near-infrared data like this, but from mid-infrared data like that. So maybe 5,000 nanometers, or light that's about 8 times longer than the reddest light that we can see. And at those wavelengths, dust does almost nothing, and young stars don't contribute much. So we only see old red stars. And if you look at in those images, the Milky Way has an X shape in its bar when viewed side on, which is very, very prominent. I don't know if you guys could see it because there's a lot of light in this room. Can you guys see that there's an X in here? Okay, great. Oh, okay, actually there's this better image here. You see like the disk, right? I said it was thinner. Look at how thin that is relative to its length, right? It's like 50 times longer than its tall.
So what's with the X?
That is a type of a class of orbits happening. So the X, you might think it's one thing, it's actually two things. I'm going to try and hold my hand really steady over here to get this right. You got some orbits that are like this, right? And then you got some other orbits that are like this. And they're even. There's an even number of them because the galaxy is symmetric between the north and south. And when you view them together, you end up with an X in combination. And now that's an explanation, but why do we care? I'll answer. Oh, sorry. Do you want to ask something?
Well, yeah, if you tilted that galaxy on an edge and you saw a diagonal view of it, would the X look like sparkles?
That is.
Or is it just two separate series of orbits that from this direction look like that?
I think, so that's a very good question, actually. I think it kind of looks like a funnel, but like a weak one in the middle of it. And then as you move to the side, there isn't going on here. It's, okay, sorry, I'm not sure, actually. But that's actually a very good question. Yes?
Are the bulge orbits nearly circular or are they highly elliptic?
They come in a variety. They're actually, so some of them are circular or elliptic, but many of them are completely chaotic. I don't have pictures of bulge orbits in here. I should give an explanation of why orbits are complicated. In the solar system, orbits are they're very simple, they're circles or ellipses. And the reason that simplicity happens is that no matter where you are in the solar system, all of the mass is within you because 99.9% of the mass is due to the sun. But in a galaxy, let's say you start off on an eccentric orbit, as you move outwards, then there's more mass within you. There's no point mass at the center. It's a distribution of mass. And that causes the orbits to take on really weird shapes. Really good question, too. So anyways, why do we care that there's an X? I show 3 different things here. This is NGC 4710, another similar galaxy with a very strong X. This is the deep projection shown below, and this is an N-body simulation with like 500,000 particles that evolve, and we see that an X emerges in the bar over time. So bars are kind of generic in simulations of galaxy formation. Pretty much anything can form a bar. But typically, to have a very strong X, not always, but usually, you need to have a very quiet galaxy. If you have a merger, it'll jumble up the orbits and you'll get a spheroid, usually. And so for the X in the Milky Way to be so strong, that means that there probably hasn't been a major merger in a long time. Do you have your hand up? Oh, okay. All right. So that's the global picture of the bar. It's solved. I think that's really cool. What's not solved Well, the detailed picture is not solved. If you look at all the stars together, there's an X. But if you break up the stars into different metallicities, let's say, they're really... So at the metal-rich stars, it's pretty prominent. This is an analysis done by Mathieu Portail. He was a graduate student in Germany, wrote a brilliant thesis. But for more metal-poor stars, the ones that are more metal-poor than the sun, it's much weaker. It's still there, but it's far weaker. And you might wonder why that is. And the answer is, don't know. That's the next step in bulge research. Okay, part 3, the ages of bulge stars. So galactic archaeology and the challenge of age dating. I used that term before. So historical archaeology has been revolutionized by carbon dating methods. No such luck for galactic archaeology. We're not successful, at least so far. When we estimate the ages of stars to try and figure out which group of stars came first, we're usually off by like 10 or 15%, unfortunately. And that does, and often more, actually. I think 10% is an optimistic estimate of the error in estimating the ages of stars, because there's no equivalent to carbon dating that could give you a 1% age. And you might imagine that we'd have more uncertainty in our books on the history of civilization if we didn't know who came first. We might be able to reconstruct it from improvements in pottery or written history when we have it, but sometimes it wouldn't be. All right, so the first evidence that the stars in the bulge were older came from Nassau and Blanco. They looked at red variables towards the center of the Milky Way, and they found that those variables had shorter periods of oscillation. So typically, so these are variables, they get bigger, 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 smaller, 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 bigger, 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 smaller, smaller, smaller. Big differences in variations. It could be 2 or 3 times brighter at the end. The periods were like a couple hundred days. And in the solar neighborhood, we get such, within like 1,000 light years of the sun, we get such variables, but we also get variables that take thousands of days to oscillate. And so they observed that difference, and they actually did not know that this was due to an age effect. But it's the first, within the literature, it's one of the first statements that's explicitly written down, which now, with what we know now about astronomy and variable stars, can be interpreted as due to an age difference, a difference in the distribution of ages in the galaxy. Okay, I'm going to skip this and this, actually. So how do we know that the stars in the center of the galaxy are older? There's a few arguments. Probably the strongest argument, I think, is this one, which has been through many iterations, but it was done really, really well by Manuela Zoccoli. She is an Italian astronomer who now works in Chile in South America, and she's probably contributed either the most or among the most that people have contributed to this field in the past 20 years. And so now we're going to look at distributions of stars. This is stars in the solar neighborhood. So you got brightness here and color here. We have faint red stars, we have bright red stars, and we have bright blue stars. Right? Now, in the bulge, faint red stars, bright red stars, and for bright blue stars, there's nothing. Can anybody tell me why there are no bright blue stars there? Yes? That's right. So bright blue stars, those are the really massive stars. They don't live a long life, right? So they die within like hundreds of millions of years. And there's just very few of them in the bulge. There might be a sprinkling of them, but it's a tiny amount. And so, right, there's a shortage of younger stars. I'll skip those quotes. Actually, this is just meant to show that there was a consensus. It's from various experts. I'll just quote Manuela Zoccoli there, since I showed her work. The bulge age, which was found to be as large of that as the galactic globular clusters, are at least 10 billion years old. So twice as old as the sun. No trace not no train, is found for any younger stellar population. Here's a more recent analysis. It's a histogram done by astronomers based in Sweden. They use the same method to look at stars near the sun here and in the bulge here. And for stars near the sun, they find all ages. They're stars of all ages, which has been known for a very long time. But the most common age is 4.5 billion years. Could you guys think of another star that's about 4.5 billion years old? Yeah. So that's another coincidence here. The sun is very typical in metallicity, as I mentioned earlier, and it's also very typical in age of the stars near it. It's kind of weird. And for the bulge, they also see stars of all ages. The sample is smaller because it's harder to measure those stars. But there isn't as big a peak at 4 gigayears. It's kind of like flat from 4 to 12. Yes?
If the bulge would appear to be denser in terms of stars,
Mm-hmm.
so there seems to be less star formation. It seems like there'd be a lot of stuff to generate star formation. Or do it's just
Sorry, can you say that again?
move out of the bulge?
Oh, they wouldn't have time to move out. For a star in a typical orbit, it would take several hundred million years. Well, for the sun, for example, it takes 200 million years to go around the galaxy, and that's a small, and then it ends up at the same spot, right? If you want a big change, you'll need a lot more time than that. So relative to the lifetime of a blue star, that's actually pretty big.
But why would there be so little star formation?
Now? Okay, I get it. Thank you. So originally, there was a lot of gas there, and the center of the galaxy, I think that's what you said, had a higher density of gas. And it does happen that when you have a higher density of gas, physically, it gets converted to stars much more efficiently. The more gas you have, if you have like 3 times as much gas, you might form 9 times as many stars in a certain amount of time. So you do run out of gas more rapidly. Once you run out of gas, you can't form stars anymore. There's other ways to stop forming stars, but that's the simplest one. And all right, so perhaps the ages are even older. I wanted to stop there, but there was a wrinkle published today, and so I decided to add it because it does inform our science. We go back to this figure here. Oh, wait. Okay. And it's kind of flat between 4 and 12 gigayears, right? So there's already a story in that it's different than what we have near the sun. But how different? And it might be even more different than they think, and I happen to agree personally. There was a new analysis that came out, I think it was yesterday or the day before, not yesterday, I had Friday or Thursday, by an Italian astronomer, Alvio Renzini. Italians have contributed a lot to astronomy, and in particular to the astronomy of the galaxy. And he says stars that are less than 5 billion years old exist in at most a trace amount, or not at all. No more than 3% of the stars. And this contradicts this image. Who's right? Who's wrong? So I think that they're wrong and he's right, but I cannot prove it right now. It's an ongoing controversy, and people have been going back and forth on this controversy for a few years. So conclusions as to the characterization of the bulge. Right? I should have brought more water. Sorry. The bulge stars have a broad range in metals abundance. You got stars with very few metals, stars that are like the sun, and stars that have 4 or 5 times more metals than the sun. It's a big range. And the typical value is about the same iron to hydrogen ratio as the sun, which is a cool coincidence. But they have somewhat more oxygen, silicon, calcium relative to iron than the sun has. Almost all of the stars in the bulge are distributed as an exceptionally strong bar. And by exceptionally strong, I mean relative to other spiral galaxies in the sky. Half of spirals have bars, approximately, so already it's stronger than half of them. But even among the half that have bars, very few of them have a bar which is as strong as the Milky Way's bar. It's not clear why that is. On the one hand, I've been telling you that the sun is typical within the Milky Way, but on the other hand, the Milky Way is atypical among galaxies. Should we interpret that or should we not? I'm not sure. And this effect is strongest among the most metal-rich stars. It does suggest that there hasn't been a merger here in a long time, a merger of galaxies. And the stars in the bulge are typically older than most of the stars near the sun. All right, that's all. Oh, thank you. Yes?
This may be a very intelligent question. What causes the galaxy to spin? What is in the center that causes all this dust and other particles to spin around?
Okay, so the question was, what is in the center of the galaxy that causes everything to spin around it?
Yeah.
I'm just repeating questions for the online audience here.
So, okay, why do galaxies spin and have angular momentum? So, if you spin something on Earth, it'll stop spinning due to drag. But if you spin something in space, it will keep spinning forever. If you're asking why does the galaxy have angular momentum, it's kind of a random thing. Some galaxies have very little angular momentum, some have a lot in one direction, and some have a lot in the other direction. And so it just happens that we live in one that has a lot in its current direction. But if you take the sum of spin of all the galaxies, it has to add up to 0. Kurt Gödel, who's a mathematician who contributed a lot to our understanding of logic, actually showed in the mid-20th century that if the universe as a whole was spinning, then not only would time travel be possible, but it would be necessary and happening all the time. And we'd have causal loops going on. Maybe that's true and we don't realize it, but probably the universe as a whole is not spinning. Yeah. Okay, so many questions.
I remember seeing a Nova episode a couple months ago about a black hole in the center of each galaxy. How does that affect the bulge?
Okay, so there is this gentleman's there's a black hole in the center of these galaxies. How does that affect the bulge?
I'm sorry, I didn't repeat the last question.
It's all right,
Thank
no
you.
worries.
So that is, that's like a major topic of research in astronomy. It's probably 10% of the papers that are published debating that point. So I cannot give you an answer. I can give you some of the answers that people have suggested. So the Milky Way does have a black hole in its center. It's about 4 million times more massive than the sun. It's pretty big, and it does turn out that for galaxies, the properties of a black hole are tightly correlated with the properties of the galaxy as a whole. Some people say that's a coincidence, and some people say that's a causal link. It's not clear who's right and who's wrong. What could be the case, for example, is that maybe you go back to the movie at the start of the proto-galaxies merging, maybe all proto-galaxies themselves had black holes, and so when they merge, their black holes coalesce to the center. And so then eventually the bigger galaxies, which are formed from more mergers, also have bigger black holes at their center. But there's huge scatter there. But there will be much better measurements of that this year. The way that's measured, there happens to be, we're very lucky, there's a star that passes very close to the black hole. It's on an elliptical orbit. And so it passes closest sometime this year. And they're taking a lot of images of it right now. And we'll have much more detail on the black hole. That'll probably be one of next year's public talks. It'll be
I
really
certainly
cool.
hope so. Yeah, that's an exciting observation coming up.
Yes.
The black hole we have in our galaxy and the bar that we have in our galaxy, how do they relate to each other? Is the black hole inside the bar at one end of it, or what?
Yes. How does the black hole at the center of the galaxy and the bar at the center of the galaxy relate to each other? So geometrically, the black hole is approximately the size of the solar system, and it's 4 million times more massive than the sun. It defines the center of the galaxy. The bar itself is not the size of our solar system. It's maybe, so half the length of the bar, as in from the middle to the end, is about 13,000 light years. So it's far bigger. And the bar as a whole is about 20 billion solar masses. So it's a totally different scale. But the supermassive black hole should be at the center. That said, you can always define the center of a circle or the center of a square. A galaxy doesn't have a very precise shape, so the meaning of the center isn't perfect. Yes.
Way back in the corner there? Yes. Not you, the other one.
Said that the black hole takes up approximately the same size as the solar system. I thought black holes didn't take up any space at all. Could you clarify that?
I'm sorry, the question was, you said that a black hole, the supermassive black hole is about the size of a solar system. He thinks that black holes don't take up any space. Can you clarify that?
All right, that's a very good question. Thank you. And so it depends how you define it. So black holes in pop culture and also in a lot of physics are just a singularity at the center, which is exactly, it's a point of no space and a point of infinite density. Another way to define a black hole is in terms of an event horizon. And that's where if you get close enough to the black hole, nobody is ever going to hear from you again. And you're done. It's the point of no turning back. And so that defines a radius, which for the black hole at the center of the galaxy is about the size of the solar system. If the sun was a black hole, that radius would be 3 kilometers, I think. Or is it 1.5 kilometers? I think 3 kilometers.
Okay, the other question in the back there. Yes, you.
So you said that stars in the bulge are in average older than those we have next door.
Yes.
Does that mean that when in the far future, when those stars in the bulge will have died, there will be a mostly empty space in the middle of between the supermassive black hole and the arms of the galaxy?
It'll look like empty space, but when stars die, they leave behind remnants typically called white dwarfs. A white dwarf might be like typically half the mass of the original star, but it's the old core of the star, and it's about the size of the Earth, and it's very faint. So you'll have a bunch of dark remnants. And aside from the white dwarfs, there will be like millions or billions of black holes that are much smaller than a supermassive black hole at the center of the galaxy, but still pretty big. So it'll look like empty space. That's a great question, actually. I'll go back to the beginning. Oh, where is it? Where's that photo? Artist rendition. Instead of this being yellow, it'll look black, but there will be a ton of objects there. It'll have about the same amount of mass.
What defines the edge of the galaxy?
What defines the edge of a galaxy?
I think, I'm not sure if there is a precise definition of the edge. And I know, for example, at a conference that I went to a couple of years ago, they debated what is the mass of the galaxy, and that depends how far out you go, because it just keeps adding more mass as you go further out. And eventually you're like in intergalactic space, and you have one point that might be closer to another galaxy, and then you move in some other direction, and it's not clear. There's no border. So in Star Trek, for example, there's like borders in interstellar space, and they police them. Or even in, did anyone watch Battlestar Galactica? There was a Cylon armistice line that was brought back. So it's like a line in space. But I'm not sure how that would work, and that'd be like a huge area to patrol.
Yeah, but as this audience learned a few months ago, the size of the Federation space in Star Trek is only like 200 light years across.
I thought it was a whole Alpha Quadrant.
Oh, no, it's only a couple hundred light years. It's really crazy. And I would also add that the edge of the galaxy is defined differently by different astronomers. Visible light astronomers might do one thing. one astronomers, radio astronomers would do another thing in terms of the edge. Yeah, he's right. There's just a lot of different variations. We have a question from online. Let's see. What are the ramifications of two bulges colliding when colliding galaxies?
That's a great question, and it's relevant because one of the reasons it's relevant is that it may happen in a few billion years here when the Milky Way and Andromeda are very likely to merge. So it does depend on the configuration that they have and whether it's like head-on or just like skidding each other, because it could be any configuration. But typically they will end up forming a bigger bulge, and statistically what happens is that stars that were in the center of their respective bulges will also be in the center of the combined bulge, and stars that were in the outskirts of their respective bulges will also be in the outskirts of their combined bulge. It's neat how that works out.
All right, other questions from here?
Is there any evidence that our galaxy is already colliding with?
Is there any evidence that our galaxy has already collided with another galaxy?
Yes. So I showed you the movies to start, so you could argue that's evidence, because within cosmological simulations that start with our understanding of the universe, galaxies are formed from mergers of protogalaxies. But maybe you want more evidence of that. And so the best evidence we have is that we do see a few small streams around the Milky Way, which they're not shown in this image. I don't know if they're shown in any of the other images. Let's see, I'll try and see if there's one somewhere. Okay, and maybe actually. Okay, so it happens that there's no streams anywhere, but around the Milky Way we actually do see a few weak streams, which are due to active accretion of smaller galaxies. But these are very minor mergers happening. It's like a 100-to-1 ratio. And whereas in simulations, we expect that at some point there should be 2-to-1 ratio mergers, 3-to-1 ratio mergers, and so on. The mergers that we're seeing in the Milky Way now are in the very, very minor merger regime, as it's called.
Okay, and we have one last question from online. How old is the oldest star in the Milky Way, and how does that compare to the age of the universe?
So that is a very good question as well. And the answer is that we can't know that well because ages of stars are only measured to about 10% precision or so. And because of that, we actually have stars for which the best estimate of the age is older than the age of the universe. But that's fine because we know that's what the measurement error is. And so we're okay with that. But eventually, as ages improve, we should not have any stars older than the age of the universe. And one thing that we'd like to find out, and for which Baltimore astronomers will take a leading role, is when did the first stars in the universe form? Was it 100 million years after the Big Bang? 200 million years after the Big Bang? That is an open topic, which maybe the James Webb Space Telescope, mentioned by Frank earlier, will help us solve within a year or two. It's one of the points of the James Webb Space Telescope.
Okay, and in the back corner.
So if galaxies that are moving away have a redshift, and you've said that Andromeda and our galaxy are going to combine, does that mean Andromeda has a blue shift?
Yes, so if Andromeda and the Milky Way are going to combine, does that mean that Andromeda has a blue shift relative to the Milky Way?
Yeah, it does. It's one of the few blue shifted galaxies. We have one more question here.
When galaxies are gobbling up other galaxies, what is actually happening to the black holes that are in them?
Typically, they will end up sinking faster because they're more massive, they will end up sinking faster, and then you'll also have a merger of their black holes eventually. And that'll make big gravitational waves. The most energetic events in the universe, within pop culture knowledge, it might be believed to be supernova, but it's actually the mergers of supermassive black holes where the energy goes out in gravitational waves. And eventually they merge, but it might be like some billion years after the galaxies themselves have merged, because it'll take time for the smaller black hole to make it to the center of gravity and encounters a bigger black hole.
All right, we're going to end it there. Irini, are you here? Anybody from the Maryland Space Grant Observatory here to take people across the street? I guess not. So there will be no observing across the street with the Maryland Space Grant Observatory. Please check their website for their Friday night open houses. Next month, August 7th, Ashes to Ashes, Dust to Dust, the fate of stars like the sun. You want to know how the story ends for our sun? You got to come next month. Let's give another great big hand. Thank you.
Audience online is wrong. There's a comment in here like, greetings from Tampa. This is fantastic, okay? There are people,